Hello class, how are you doing? In this video we're going to talk about surface area. I would like for y'all to know, when I talk about surface area, it is possible that we speak about surface area which is including the top and the bottom and the side. On the side they call lateral surface area. But when we talk about the total surface area is a lateral surface area plus the other piece, which in this case is two circles, one on the top, one is on the bottom. And this is nothing except a cylinder, and cylinder is created by taking a rectangular plane and fold it in a circular shape, and that become the circumference in the bottom, which is 2 pi r, and that become height. Therefore the lateral surface area is 2 pi r times h, and then if you needed the total surface area, you have to add the top and bottom. We have many formula to find the surface area of a regular geometric shape. But what happens if the shape are not regular? If you remember in calculus 2, we took some graph like y equal to x squared, and maybe we restricted its domain of the x from 0 to 2, and we take that piece of the graph and rotate it around the y-axis, and you create a surface of revolution. But in here the surface area, the circumference still is pretty much 2 pi r, but as you know the radius changes, but the height is not a straight line, it's an arc length. Therefore that's where it comes in place of the arc length. Interest of the height is the arc length, and the arc length depends if you are doing it respect to x or y or t. If it was respect to x, it was 1 plus y prime squared dx. If it was respect to a y, that was 1 plus x prime squared dy. If it was respect in a parametric form from t equal to a to t equal to b, it was the square root of dx over dt squared plus dy over dt squared dt. Then because the radius changes, you find the surface area of one of these representatives, and you say 2 pi r times ds, the arc length of it. And in here, the arc length in here, it can be divided to having the y fixed. And your radius is a direct distance from the y and is x. Therefore, the surface area, if I take my y fixed from 0, okay, in here, when x is 0, y is 0, and when x is 2, y is 4. You go from 0 to 4 because I'm doing it with respect to y, and you have 2 pi, but your r is x, but this one I'm making my y fixed, therefore it becomes 1 plus x prime squared. Everything looks good except I have to change these x's in terms of y, but this is my equation on my graph. I'm going to solve for x by taking the square root. Therefore that's my x, but my x prime is 1/2 y to the power of negative 1/2, and it becomes 1 over 2 square root of y, and when I square it, it becomes 1 over 4y, and when I add 1 to this one, it becomes 1 plus 1 over 4y. And when I take the square root, it becomes 4y plus 1 over a 4y. This is the one goes under the radical. Then I have my surface area equal to 2 pi from 0 to 4, and I have an x. Instead of x, I put the square root of y, and then this goes under radical, and I put the numerator under the radical, and the denominator it becomes 2 square root of y dy. This dy is gone, the 2 is gone, and I have nothing left except pi 0 to 4 square root of 4y plus 1 dy. In here I can do chain rules, and I said my u is equal to 4y plus 1, and my du is 4 dy. Therefore I do need a 4 here. I multiply by 4 and divided by 4. Therefore my answer would become pi over 4. This is u to the power of 1/2. It becomes u to the power of 3/2 divided by 3/2, which is times 2/3. I'm not going to change it back to 4y plus 1. I'm going to change the limit. Therefore, when y is 0, my u is 1, and when y is 4 is 17. Therefore, my answer is going to be pi over 4, 2 pi over 12, which is pi over 6, and I have 17 to the power of 3/2 minus 1. And that would become my answer. But the problem is here that was the surface area of the lateral surface area. If you want all of these, that become pi r squared, and your r here is 4, and that becomes 16 pi, and you can add it. But sometimes this is not my concern. Sometimes I have a region here, and I don't know what my region would look like, but I have some kind of a region here, and that region I'm going to have a surface above, I'm going to have a roof above of it, and that roof might give us that roof might provide to us by a function of y equal to 25 minus x squared minus 4y squared. Therefore, you know when xy is 0, your z is 25, and this one is in the zx direction. In a zx plane is going to be, the trace is going to be a parabola. On zy is going to be a parabola, but xy is going to become a ellipse. Therefore, this is nothing except elliptical paraboloid, and that elliptical paraboloid is going to produce some kind of a surface on some kind of a cover over my region, and I want to know what are those surface area. In here I'm going to go draw a whole bunch of lines which they are same thickness, the distance between them are the same, and these are called my delta x, and I'm going to do it parallel to the y, and I'm going to do a whole bunch parallel to the x with the same distance between them. Then what I'm going to do, I'm going to take one of these rectangle, and I'm going to project it over my roof, and I'm going to find the area of that tangent plane. Therefore, the area of that tangent plane, which is cover part of my roof, then if I sum it up, it gives me the surface area for the top. The question is here, how are we going to find that area? That area can be done by finding these two vectors, which I'm going to call one of them v, call one of them u, and I'm going to cross it and find the magnitude. Therefore, I know the area of that parallelogram is going to become the magnitude of u crosses with a v. Then that's only for one of them, and that's the tangent plane. Then I'm going to sum it up. But somebody said, how do I find those vectors? Therefore, I know every one of them have same y value, because the y here is whatever that y is The y of all these points are the same. Therefore, for every one of these x, you're going to have a different z value, even though all the y value for that one is going to be the same. For this line, every one of the y's are different, but the x's are the same. Therefore, the change in z, we use differentiation and say the total differential by applying the x and a y into my function, I can find the change in z. Therefore, what is the change in z right here? Is a partial derivative of x dx plus partial derivative of y dy. But you know, when you're talking about these this delta x right here, your y is fixed. Because your y is fixed, the partial derivative of y is going to be 0 because your y is constant. Therefore, that vector right here, which is a vector u, the x of it is provided by the delta x, the y coordinate is 0, but the z of it is going to be the partial derivative of x dx. But the vector v, your x is constant, therefore the rate of change in respect to x is 0 because you're taking your x as a constant. But whenever I do the respect to z, the total differential, because my x is fixed, this portion, the partial with respect to x, because it's a constant, is 0, you have your z is going to be f of y dy. But the middle is going to be nothing except the change in y value. Therefore, I have two vectors, change in x, no change in y, change in z, no change in x, change in y, and change in z. Therefore, I got the two vectors, and I'm going to cross those vectors by I, j, and a k. Therefore, your I can be here for the vector u is going to become a delta x, and 0 and f of x delta dx, or delta x. In here, it doesn't matter, that should be a delta x right here, and that should be a delta y here, because I have not put the inside the integration sign. In here, doesn't matter if you write the u first or v second, because eventually I'm going to find the magnitude. This one is 0, the v is 0, delta y, and that's going to be partial derivative of x, partial derivative of y, dy. Therefore, what is my I component? My I component, you eliminate this row and a column, you become negative partial derivative of x, delta y. And what is a j component? You eliminate these two, it becomes delta x, delta y, partial derivative of y. And this is my j component. And my k component is delta x, delta y, and that's your k. If I take the magnitude of that one, that becomes the area of that tangent plane. Therefore, the area of the tangent plane is, take the magnitude, and when I square that one, the negative become a positive, and it becomes partial derivative of x squared, delta x, delta y squared, plus, when you square the negative, it becomes a positive, partial derivative of y squared, delta x, delta y squared, and this one is become delta x, delta y squared. And I see a common factor between all these three, and all of them have delta x, delta y as a common factor. Therefore, I see the area of a tangent plane is the square root of partial derivative of x squared plus partial derivative of y squared plus 1, and delta x, delta y is outside. And sometimes we write this one as the partial derivative of x squared plus partial derivative of y squared plus 1, and this is nothing area of the region. Then, if you want to really find the surface area, is going to become the sum of area is a double integral, and that's becoming your region of f of x squared plus f of y squared plus 1. I'm sure some of you are going to find some of you already see what this one is. If I write my z equal to f of x and a y, and if I write this one explicitly as a function of three variables, therefore I can write this one x, y, and a z, and I take my z to other side, or you can take f of x, y to other side. It doesn't matter. But if you take the gradient of a w, that becomes partial derivative of x plus, because remember, that's your w, x, y, and a z is a partial derivative of x plus comma partial derivative of y comma partial of z. Because z has a coefficient of 1, the partial derivative with respect to z is 1. Therefore, if I take the magnitude of the gradient, that become exactly partial derivative of x squared, partial derivative of y squared plus 1. And that pretty much is the magnitude of the gradient if you solve for z, if you solve for the w in terms of three variable explicitly. But remember, when we talk about those surface area only can be applied when your surface is not parameterized, is written explicitly in terms of x and y, and that is the formula for your surface area. Then let's make an example. Let's say I have a z, and the z is 4 plus x squared and plus y squared. Okay, and let's talk about this, because the graph of this one is going to become a parabola if the y become a constant, and that become a parabola if x become a constant, and it become a circle. Therefore, when x and y are 0, the z is 4. Therefore, when the z is 1, that become a negative 3. Z cannot be 1. When z become 2, see, you have x squared plus y squared equal to, I take this 4 to other side, z minus a 4. If z is 4, yes, we have a point. But when z is 1, 2, or 3, you don't have a graph. Z has to be 5, 6, 7, 8. Therefore, you know over there you're going to have a hyperboloid. I'm sorry, paraboloid. But somebody going to say, this one is your z value, this is your y value, this is your x value. I want to know this one cover up what region. I'm going to say the region this one is going to cover is a unit circle. Therefore, if this is a roof over a unit circle, that unit circle become my region. Therefore, that region is going to provide us with a lower limit and upper limit. Therefore, that region is from negative 1 to 1, because I make my x fixed. My y is from negative 1 minus x squared, and this one is 1 minus x squared, and dx, dy, dx. That's my area. Right now, I need the gradient of that one. It doesn't matter if you bring the z to this side or x squared plus y squared and 4 to other side. Whenever you find the gradient and you find the magnitude, you got to square it. Therefore, what is the partial with respect to x is 2x squared. Respect to y, 2y squared. And this one, when the z comes to side, become a negative, but negative 1 squared still is a positive. Therefore, that surface area is become equal to 4x squared plus 4y squared plus a 1. And in here, that's my region, and that's my dA. My question is here, is impossible to integrate this one, because if I want to do it with respect to x, I need the x outside. If I want to do it with respect to y, I need the y outside. here is going to help me if I can change the system from a Cartesian to a polar. And if I factor 4, that becomes x squared plus y squared plus 1. Therefore, your inside radical becomes really 4r squared plus 1. Therefore, instead of a dy dx, I'm going to put r dr d theta. But what am I going to do with these? This is nothing except a unit circle, which you do require from 0 to 2 pi. But how about the r? This r, the radius is the same as the r of the polar coordinate because it stems from the pole. And all these r's are exactly the same as the r of the polar, and is always 1, a fixed number. Therefore, the lowest is 0, the highest is 1. Then I'm going to go integrate this one from inside, and when I integrate that one from inside, I'm going to make this one a u. 4r squared plus 1 is a u. Their du is 8r dr, and I do need an 8 in here, therefore I'll put a 1/8 here. Therefore, the inside integral become the square root of u du, but this 1 and 1 belong to the r. But if I bring the 0 and plug it in for the r here, my u become 1. And if I put 1 in here, that become a 5. Therefore, I'm going to integrate the square root of u from 1 to 5, and that's become u to the power of 1/2 plus 1 is a 3/2 times 2/3 from 1 to 5. Okay, I got that answer. Then let's go to outside. The outside, I have a 1/8. This number is 2/3. The 2 comes in here, and 3 times 8 is 24. Therefore, is 1/12. This is 5 to the power of 3/2 minus 1 to the power of 3/2. Then I'm going to integrate it from 0 to 2 pi. The only thing is left is d theta. And this one is theta from 0 to 2 pi. And that is 1/12 of 5 to the power of 3/2 minus 1 to theta, 2 pi. That 2 come over here, it become 2/12. It become power 6 of 5 to the power of 3/2 minus 1. Then that's become a u squared because it's the surface area. Therefore, you have to remember surface area is nothing except a roof over a certain region. The region going to provide you with a lower limit and upper limit, and the gradient of that one in term of x, y, z is magnitude. We're going to give you the what? It's going to give you the integrand, and then you can find the surface area very easily. Please remember, this is only valid when your function is explicitly in form of x and y, as it is not parameterized. Thank you.